Okay, I think we can start with a bit of delay because of the raining, let's say. So good morning, everybody, and welcome to this symposium on future internet. We're particularly focusing on security aspects, but in general on opportunities that the future internet architectures might bring, and we as researchers and industry might exploit. It's my pleasure to leave the floor now to the Vice Rector for Technology Transfer of University of Padua to give a welcome.
Good morning, ladies. Examples of such a kind of side effects of research are well shown by the speakers of today, who are owners of a lot of patents and founders of spin-off companies. Unismart Padova Enterprise, a limited company 100% owned by our university, is another example of how our university is improving technology transfer activities. It serves as a bridge between researchers and outside entities interested in developing and commercializing the results of academic research, supporting with the specific tools younger researchers and the laboratories to improve the number and the quality of collaborative research, to find equity for their spin-off companies, and to license intellectual property. Cybersecurity and privacy are emerging topics at the Industry 4.0 paradigm, and many research groups of our university are worldwide recognized like leaders in these sectors. But again, this knowledge and expertise should be used not only for fundamental research, but also for helping digital transformation processes, the small and medium enterprises of our region and country. The SMACT Competence Center, SMACT, you know, means Social, Mobile, Analytics, Cloud, and Internet of Things, is the new tech transfer community and center for digital transformation, constituted by 9 universities, with Padova as the leader, 2 research centers, and more than 30 technology providers and companies, with the aim to evangelize industry and entrepreneurs of our country to the manufacturing processes and products of future. Social, mobile, analytics, cloud, and Internet of Things are enabled technologies which need to guarantee privacy and to be used and developed under a high level of security. Hacker attacks are more and more frequent, and the researchers and technicians are asked to fight a real war against them in order to provide to industry, government, banks a minimum level of security in managing and exchanging data. Exchanging ideas, discovering new algorithms and the method, sharing knowledge and practices in this field is the goal of this workshop. I would like to thank Professor Mauro Conti, the chairman of the event, and all the outstanding speakers coming from different countries. Finally, I would like to thank Cisco, in particular Enrico Mercadante, which is present not only as a partner of the conference, but also with some interesting speeches which can open the mind of young researchers to new research topics. Thanks to all of you for choosing our university as the perfect location to present the results of your outstanding researches. Enjoy the workshop.
Thanks, Professor Dughiero, for the welcome on behalf of all the university. Now, as you know and seen from the logos and advertisement, This symposium has been organized in conjunction between the University of Padua and Cisco, and in particular my research group is affiliated with both the Department of Mathematics and the HIT, Human Inspired Technology Research Center. The head of the Department of Mathematics could not be here today, and we have also the director of the HIT. Thanks.
Just a quick welcome to all of you. It's a great pleasure to host this symposium, and I want to really thanks the Cisco group for this occasion that offered to us and to our research center that is quite a unique center in the Italian and European panorama of research center, because it's a peculiarity to offer this two different approach to new technologies. The most classic, so the informatics, engineering, but with this approach that is strongly human-centric. So because of this, we have this name, Human Inspired Technology Research Center. So we are a group of 70, 80 professors coming from very different disciplines and 9 different departments. And we offer this opportunity to join this different knowledge, this different background in a complete vision of technology and future technology. So especially for the internet, it will be a great opportunity and a great challenge to research, to investigate together, psychologists with informatic computer scientists. And I think this occasion that Cisco offers us is I hope it will be one of the first occasion and one of the first grants that in some way will be continued in the future, because of course we are just the beginning of our path, and the challenges that in the future we will have to deal with are absolutely difficult and complex. So we really need the collaboration of all the companies and the different labs that are part of the University of Padua. So really thanks to our sponsor and to Mauro Conti to create this opportunity to exchange this day devoted to the future of the internet. As you know, this is also a very important call inside the European Commission actions. So we are also dealing with European proposal and project that in some way deal with the topic that today will be discussed by all of you. Thank you also to all our speakers. We have several invited speakers today from Italy and from United States. So I think the day will be very interesting from the scientific point of view. Thank you all to be here today, and thanks Mauro for the organization.
Okay, we don't have much time left, but I see the keynote speaker is not yet in the room, so maybe I can take a couple of minutes more. So I would like to spend a few minutes to introduce you our research group. Some of the main activities we do, one of which is definitely working in the security of future internet architecture. And then I would like to introduce this event telling you a bit the story of the collaboration. In general, our work in future internet architecture and our collaboration with some of the people involved in this event, and also in particular with Cisco. This, if you reach this point, maybe you know exactly where we are, and I don't need to tell you something more about the University of Padua, but we are definitely one of the best university in Italy for the quality of the research, and I don't know how many of you are actually coming from outside Italy. If you are here, there is a chance to visit, for example, the main building of our university with the podium from where Galileo was teaching. And this is the justification for the acronym for the research group, which is named SPRITZ. You probably know it's also used for something more practical here in Padua, but this is a, let's say, justification. So we do security and privacy through Zeal, and this is the actual meeting of the group. The research group currently counts several people. It's very hard to keep this slide updated because people come and go and get also short visiting period in our group. But we have now several postdoc researchers, as you see from the slide, coming from all over the world, and several PhD students, and many of which are actually involved with the Brain-Mind Computer Science PhD school, with this, which is a PhD school inside the HIT Research Center. And also, I mean, in our research group, we host a lot of master thesis and visiting internship for, of course, for students of University of Padua and foreigners. And actually, some of this history that I will tell you in a while about our collaboration and work on future internet architecture started with some master thesis. These are some of the main collaborations we have, both from the government point of view and national, international government agencies, and collaboration with companies, one of which being actually Cisco. There have been several reasons for which we have been in the news in the past, so far only for good reason, likely, but you never know. Let's hope for the good. And we have done some work on authenticating users on mobile devices that ended up also in the New York Times as one of the promising way to modify the future, to improve the future. Several work we have done on Android security. As you can see, future internet architecture, but we'll discuss this in a while. We do research in software-defined network, which is another way of designing the internet of the future. And we had some other events in the past. Similar to this event, we organized actually PhD school, so school for researchers on mobile security, social network security, and so on. And we've been awarded with several prizes. In particular, these are some of the prizes we got with master's thesis of the student from the CLUSIT, which is Italian Association for Computer Security. I'm not going to bother you with many details, and some of the topics we work on are summarized in these slides. So we work on mobile security, future internet architecture that is mostly discussed in this symposium, side and cover channels. Some of those research actually got quite a bit of visibility lately, also from Forbes, from BBC have been featured. Social network aspects, about, I mean, several aspects on security and privacy on social networks, and also the Internet of Things, which somehow also involves designing the future internet architecture. So I'm not going to bother you more with the details of the research group. What I want to do now is just a brief introduction while we wait for the first keynote to arrive. I will try to contact him. Is a brief history on how we got involved in this domain of the future internet. We work mostly in security, and Professor Zudik, that will give the first keynote, will probably give you I mean, a more proper introduction of what is the motivation of designing the internet of the future. But I want just to summarize our involvement. So how our group met the future internet, or actually how we build the future internet, because we are part of this process. Again, I'm not going to bother you with the history of internet, all the details, ARPANET, this and that, but you probably know, long story short, that the internet was designed conceptually working similar to the telephony system, because we were making simple connection with a host, asking for a service and closing the connection. So there have been a lot of changes from that time, and the way we use internet today is completely different. We all have smartphones, we all have a lot of services running on our device, and so on. And this, of course, call for a strong change of the architecture. We should not, or we cannot keep using the same architecture that was designed to serve the phone service for today's purpose. But again, this will be, I'm sure, probably introduced by Jin, that thanks just arrived here. So I want just to start with this, and I mean close this introduction actually. with a very short story on what has been our role and our involvement in this aspect of the security of the future internet. I made this slide, this night basically, and tried to recall and put together all the pieces. So as a disclaimer, probably dates and facts are not very precise, but this gives you an idea of what happened. I recall that everything, I think, on our collaboration started with the first visit that I did to Jean's lab in 2012. Actually, I have also to thank the University of Padua, because I was here just for a few months and I got, let's say, a small grant that allowed me to pay this visit to Jean's research lab. And with that, we started working on some of the first research aspects. That was cache privacy. Details will be given later. And then at that point, two, let's say, key people were involved, were two master students. One is Alberto, which is here in the room and is one of the key people in this collaboration. And also Moreno Ambrosin. They were both master students. And Alberto was also involved in visiting Jean during that period. And then he moved on to the next step with a PhD. And during the PhD, Alberto was again visiting Jean, visiting Cisco in Boston, visiting Cisco in Paris. And as you can see at the bottom of the, at the end of the line, when Alberto graduated, it actually moved to Cisco. So just changed the head. And over time, there have been several visits that Jean made us this week, visiting our university and our research group, pushing on the collaboration, involving more and more students in this. At a point, our university joined the NDN testbed, which is one of the, NDN is one of the projects trying to implement the information-centric concept. And we started being part of the testbed. At that point, we were definitely the first node in Italy and one of the few nodes in Europe, while there were already several nodes in the United States. And over time, as you can see, there was also some stronger interaction with the Cisco Paris lab. There was an event that we attended together with Alberto and Moreno in Paris, and also there we kind of started more the collaboration with Giovanna Carofiglio, which is kind of co-organizing this event together with me. And also we had some collaboration with Ralph Droms, that was Cisco that time. And also Ralph came here to give a colloquia Patavina, one of the colloquium hosted by our university. And lately, also Fabio De Gasperi, which is another PhD student, spent a visiting period at the Cisco Paris laboratories. And finally, we also got a research grant that's for which we are very thankful to Cisco. And it's actually also thanks to this grant that we are organizing this workshop. And also thanks to this grant, we were able to make the collaboration and the work in the future internet design even stronger. We, thanks to that grant, hired also some people like Eleonora, which is also here in the room. And a lot of other people were involved in the collaboration, a lot of other students. And this led to this workshop and this symposium. So again, thanks for being here. This is a quick overview of what is expected for today. So I don't know whether we are on time. We started late, but we got on track very fast. So first we start with a keynote from Jean Sudik, University of California, Irvine. Then there will be, I guess, a quick coffee break. And then we have industrial session by Enrico Mercadante from Cisco. Thanks again for being here. And then we have some other research session, one before lunch, given with two talks, one by Eleonora and the other by Alberto, again, now with Cisco. And after the lunch, there will be first another session with two guests from ETH Zurich, also working on similar aspects or different direction on the future internet architectures. There will be another keynote by Professor Zorzi from our university. And after the coffee break, there will be a few other talks by PhD students, Hassan, Fabio, and Ankit. So again, thanks for being here. And also let me take this chance to, thanks of course the university for all the support and organization, and also huge thanks to all the research group that is behind this. Not just doing the research and good research day by day, but also to support all the organization of events like this that takes, of course, a huge effort. So thank you everybody, thanks you for being here. And I would start with the first keynote. Maybe you can take a couple of minutes break, but then we'll start with the first keynote by Professor Jean Sudik. Thanks a lot for coming, Jean. Okay, I think we can start now with the first keynote. So let me give just a I will try to make it very brief introduction of Gene Sudik. Actually, for those in the field, is really a person that needs no introduction, seriously. But I see a lot of young students that maybe need to know something more. So Gene is a Chancellor's Professor in Computer Science at the University of California, Irvine. He obtained his PhD in computer science from University of Southern California in 1991. Before going to UCI, he was with IBM Zurich and USC. His research interests include many topics in security, privacy, applied cryptography. He is a Fulbright scholar, Fulbright specialist, twice fellow of IEEE, fellow of IEEE ACM, and member of the Academia Europea. From 2009 to 2015, he served as editor-in-chief of ACM Transaction Information System Security, which is one of the major journals in computer security. And I would leave you other details and the floor for this keynote. Thanks a lot for being with us.
Thanks, Mauro. Do I need a microphone, or can I need for recording? Because I'm not a quiet person. Okay, thank you for the introduction. So this talk will be a bit technical. I don't know, maybe more technical than a typical invited talk should be. So I apologize in advance for that. So this is joint work with, actually all three of those people are alumni of my lab. One of them has been working at Xerox PARC for a while, that's Ersin Uzun, and the other two recently graduated in the last couple of years, and one is working for this giant vacuum cleaner called Google. It sucks up all PhDs, and the other one is working for Apple. So again, I want to thank Mauro for inviting me here, and I'm glad to see so many people in this beautiful room where I've never been before, despite having visited Padova many times. So this work will be, never mind the title, the work will be on something called stateless forwarding, stateless processing in content-centric networks. So I will first introduce content-centric networking, but briefly, and discuss how it uses its what's called stateful forwarding plane to forward and route packets. Then I'll discuss something called the interest flooding attack, which is probably the worst feature or the worst security problem in context-centric networking. And then I introduce a potential mitigation approach called, or alternative design, called stateless content-centric networking, and give you some results from the experiments. And we'll conclude and go to break. So there is some terminology first. So you may have heard the terms information-centric networking, and you may have heard the term content-centric networking, and maybe named data networking. So they're kind of concentric definitions. So information-centric networking is the broadest concept, and then content-centric networking is a type of information-centric networking, and then named data networking is an instance of content-centric networking. And there are two, let's see, I think I have actually, yeah, I have some graphics for visual type learners here, right? So that's how it goes. And so CCNX and NDN are two concrete software suites or implementations of content-centric networking. They're very, very similar. They have the same roots. One was started at Xerox PARC maybe 10 years ago, 12 years ago, and then they kind of diverged. The NDN is now at UCLA, and CCNX has changed the ownership from PARC to Cisco, and God knows what's happening there. Well, maybe we'll hear more later on today. And they're close relatives, and for the most part, everything I say applies to both CCNX and NDN. And I should say that at least last I heard, there were some unification or hybridization efforts underway in industry and academia. So proceeding to the overview or background on what is content-centric networking. Well, it's the kind of networking that, well, makes content number one player, right? Instead of making interface addresses or IP addresses the most central part of the architecture, like today's IP, content-centric networking emphasizes data. Information, data, content. Those three words are interchangeable. Why does it do that? Because the original internet was designed for point-to-point communication, was designed mainly for three things: to share scarce, expensive resources, like have remote access to supercomputers or other expensive equipment. This was the case in 1970s, 1980s. Two, to transfer data sets or files, large files. We still have that. It's called FTP. And three, to support store and forward email. And we still have that today. And it is not going away for some reason. It still accounts for some small part of internet communication. But ever since then, things have changed. In the mid-90s, with the advent of the web, we started seeing more and more demand for scalable, very, very scalable content distribution. Right? When the first viral posts started happening, and the first dancing kittens and I don't know, card-playing monkey videos appeared, the first time some crazy lady in Scotland started singing beautifully, and everybody wanted that video immediately. That's when we started seeing that today's internet doesn't work well for that kind of massive content distribution. Okay, because it wasn't designed for it. So what content-centric networking tries to do is to address that problem, right? Of massive, that's its claim to fame. And what it does is it says, look, we won't have hosts, or we won't have explicit notion of hosts and interfaces. Instead, we will only have content. And every piece of content will be uniquely named, routable, and addressable. Okay? There are, again, no explicit host or interface identifiers. They exist, but they're not explicit. The key elements of content-centric networking, at least the kind that I will talk about, is that the network has memory. What does that mean? So today's network, today's internet has no memory. It doesn't keep state. Now, if you really understand how today's networking works, maybe you will argue with me and say actually that it does, because in order to route IP packets, routers need to have some state, but that is the state called FIBS, or forwarding information base, where routing information is stored. So a packet comes in, IP datagram comes into a router looks up the destination using longest prefix match in its forward information base, and which tells it where to forward the packet next, or to drop it. Now, one packet doesn't affect the next packet, or is not influenced by a previous packet, which makes the internet pretty much stateless as far as packet traffic is concerned. Okay, so I mean, when I say stateless, I mean traffic does not really affect the state of the internet, in the middle of it. But content-centric networking changes this paradigm into a stateful internet where routers acquire state. In other words, the network starts having some memory. Specifically, what that means is that routers are now expected, not required, but expected to have some form of a cache. Why? Because for very, very popular content, that's how the rationale goes, it pays to store that content in the cache of a router so that subsequent requests for that content can be satisfied from the router rather than going all the way to the place that produced that content. Okay, because if you think about it, what happens today, let's forget about CDNs for a moment, but if there is a viral video that somebody posts on YouTube or on their own homepage, and millions of people, like bees on honey, start requesting that video at about the same time, tremendous congestion happens. Okay? And things can even grind to a halt. It's similar to a denial of service attack. In some ways, it's indistinguishable from a denial of service attack. Distributed denial of service. So if you imagine what would happen in context-centric networking, such congestion cannot occur or should not occur, because only the very first few requests would come to the source of that viral post, and then everything else after that would settle in the caches of internet routers, and subsequent requests will not reach the destination or will not reach the producer of content, and will therefore dissipate congestion. So if you love this fairy tale, it's a beautiful one. It says that everybody will live happily thereafter, at least with respect to content distribution. So coming back to the kind of state, that there's two types of state that CCN envisions. One is the cache, which means a router is recommended, is not mandated, but recommended to have a cache. The size of the cache is not mandated either. You can have a large cache, a small cache, but it's supposed to have a cache. And whenever requests come in, they're called interests. Whenever requests come in, a router should first look up its cache and say, oh, is the desired content already here? If it's here, that's it. Everything is short-circuited, and the content is returned towards the requester. The requester is called the consumer. In addition, there is another data structure, another kind of a fast cache called PIT, Pending Interest Table. And that structure is designed to keep state about the requests that have not been satisfied. That is something called pending interests. So when a request or interest comes into a router looks up the cache, says, do I have this content here? If the answer is no, it then looks up, in fact, it can do it in parallel, it can look up its PIT, and say, do I have already a pending interest for the same content? If the answer is yes, then no need to forward it further, right? Because there's already a pending interest. So what it does is called collapses the interest and just remembers that it came from a particular interface. Now, if you're following my description, what happens is, this is a very seemingly nice feature, because what happens is that if you have closely spaced, very closely spaced in time, or almost simultaneous interest for the same content, coming into the same router, only one will be forwarded, the first one. The subsequent ones will be collapsed or aggregated. Now, thereafter, when the content returns, right, when the content is returned, and a router forwards the content, it knows which interfaces to forward it out on, because it remembered from collapsing. Okay? So these are two data structures, or two caches of sorts, that are introduced as part of the content-centric networking architecture. The cache itself, the content cache, is optional, but the pending interest table is not optional. So, as I said, content is king, first-class object, and it's named and addressable and routable. So there you have a very simple example of content name. There's no limit on how many components a name can have, or how long the overall name is, or how long the overall a single component can be. So you see a longer example at the bottom of the slide, right? This would be something if you presumably went to see a list of my current students, right? That would be a hypothetical name of that content, right? Now, if it helps, if you've never heard of context-centric networking, one way to think about it is like URLs and web pages, except not at the application layer, but at the network layer. So yes, if you are already thinking that this kind of crazy long names are visible to the network, you are right. They are supposed to be visible to the network. So the network doesn't see 32-bit IP addresses. What the network sees are these things, which could be very short, like /my/data, or very long, like the one at the bottom of the slide. Okay. So the other thing is that unlike today's internet, CCN has some security features. Actually, it really has one, and it's an important one. And it says that content must be signed or authentic. But really what it says, content must be signed. Signed means every piece of content must be accompanied by a digital signature generated by its legitimate producer or publisher. Right? These two words are interchangeable. So the publisher must use his private key, and I hope everybody knows at least a few terms from cryptography. So there's a public key that corresponds to every producer of content, and there's a private key that only that producer knows. So that producer generates a signature on every piece of content it produces, and anyone who has the public key certificate of that producer can then efficiently verify the signature. Okay? Are there any questions so far? Be happy to take questions. Okay. So, and then there's some magical way of distributing public key certificates. And if you know anything about security, that's the kind of dirt we usually sweep under the rug so that nobody asks difficult questions. Okay? So it's not unique to content-centric networking. This is a headache everywhere in network security. So today's internet has only one type of packet. It's called IP datagram or IP packet. CCN has two types of packets: content and interest, because it's basically a request-response paradigm, right? So what we have there, well, we have the name, we have the data, the actual payload, and we have a signature. There are some other fields, but they're not important for the sake of this presentation. So again, every content is named. Every content must have some body, right? Have some information, and every content must be signed. Now notice that content has no source address and no destination address. Right? It has some fixed header and these other fields, but they don't say where it is coming from and where it is going to. It does say who produced it, but this is not the same thing as knowing where it comes from. So now if you understand this correctly, content does not have to come from its producer. It was originated at its producer, but it may be fetched, it may be found many places, including some router caches in the middle of the internet or at the edges of the internet. So when you see a content packet of this sort, you don't know where it came from. You know where its origin is, but you don't know where it came from right now. And you also don't know where it's going because it doesn't have any information about who requested it. This is by design. This is on purpose. Okay? So, interest. Now, I'm going a little bit backwards. I'm showing you content before I show you the interest. The interest is the request packet. Remember, all this is at the network layer. This interest packet has a fixed header, has the name, right? This is the name of what is being requested. And it may have optional payload. There's some reasons, good and bad reasons for that payload, but it can have some other information in it. But notice, no source address, no destination address. Now, if you are particularly alert and not jet-lagged like me, you probably already understand why that is. First of all, there's no need to have the source and destination address if you followed my description so far. And second, it's good for privacy. And privacy is good, right? Because let's look at today's internet. You see a packet in the middle of the internet, and it carries source and destination addresses. And if you have the standard internet tools at your disposal, you can quickly check where the source is and where the destination is, and which organizations own which IP address, right? So you actually can learn quite a bit from looking at a random IP packet in the middle of the internet today. Whereas here, when you look at the interest packet, you don't know where it came from. You may know the direction, but you don't know where it came from, and you don't really know where it's going. You might know the next hop, but you don't know where it's going because a copy of the desired content can be found many places. And it also has no signature, right? So there's no security of the interest packet. And that's an interesting feature, or lack of feature, because if there was a signature, it would tell you where it came from, right? But since there's no signature, you don't know where it came from. And now if you remember my description of these pending interest tables, right? Remember a few slides back, I said there's this pending interest tables. Every router has a pending interest table. And so if you now combine that description of pending interest table with these two packet types that I described, you'll see why you don't need to have source and destination addresses. Because if you studied networking some time ago, or if you were just a curious person, you may have heard of things like virtual circuits. Classical networking approach. Well, if you know what a virtual circuit is, CCN uses what's called one-time virtual circuit. So the interest packet basically establishes like pebbles or state in the routers it traverses, and the content packet erases that state as it hops back. So, which results in a kind of a one-time virtual circuit. Right, so one very simple way of looking at it is a consumer, and this is the name of the entity that issues an interest. It's not a host, it's a role. There may be a host here, there may be some host, some computer that issued an interest, but that computer is not a consumer. That computer only plays the role of the consumer in this interaction. So it issues interest, and then the network is supposed to find this name somewhere. Now it may find it in the network, or it may find it at the producer, in the worst case. Right? In the worst case, because in the best case, there's something closer, nearby, which has a copy of content. Right? But if it goes all the way to the producer, then the producer will return it, and it will get delivered to the consumer. But what this picture does not show, actually, this one does. This picture shows it better. What happens is when the content goes from the consumer to the producer, you see these little red circles, they represent pit entries, right? These pebbles that are left along the way. And when content goes back, it actually hops along the reverse of that same path and actually erases pit entries as it goes. But at the same time as it erases the pit entry, it also allows the routers to cache the content that they forward, so that subsequent requests can benefit from the cache. Right, so this is kind of blurry, but within a router, this is what happens. An interest comes in, the router says, is the interest in the pit? It's not the same interest, but is the interest for the same content in the pit? Okay? And it also asks, is it in the cache? And it can do these things in parallel. There are some trade-offs in doing them sequentially, but you could ask these questions in parallel, right? And if the content is already in the pit, I mentioned what happened, right? If the interest for the same content is in the pit, then there's something called collapsing that takes place. If the content is already in the cache, then it's just turned around and set back. But if the answer to both questions is no, then you create a new pit entry, which I call leave a pebble, and forward. And when the content comes back, eventually, you have to look up the pit. Right? You have to associate the content with the corresponding pending entry in that table. Okay? And then optionally cache the content for future requests, and then forward. Now this forwarding may actually happen to more than one interface, right? At least one, but could be more than one because if collapsing occurred earlier. Any questions? Okay. All right. So this, yes? Totally agree with you. Yes. It's coming up. Yeah. Definitely, definitely. Okay, so this way of this content centricity, does it imply the need for these two structures, for the pits and the caches? And for most people, for most networking researchers who know this architecture, I think the answer is yes. Now, I'm not a networking person, I'm a security person. I'm also a bit of a contrarian. So for me, the answer is maybe. And the other question we can ask, because right, you can still imagine a content-centric architecture which does not have these structures. Right? You could still address, route, and name content without keeping caches or without having pending interest tables. The other question, for me, a fundamental question, is this kind of stateful forwarding, right? This is this process that you saw on a previous slide. This is called stateful forwarding. Stateful because routers keep state. So is this stateful forwarding actually beneficial for the internet? Not for some private network. Maybe the answer for a small private network may be always yes, or always no. But the question is, what about the internet with highly sort of heterogeneous traffic, different needs everywhere, and very sort of volatile congestion and flow control situation? Is this beneficial? Is it always beneficial, sometimes or never? These are the questions I'm asking. And I'm not going to actually answer them even at the end of this talk. These are just, to me, an important set of questions. So let's consider some things about a stateful forwarding plane. The way that I describe this internet architecture is that, right, there's something called there's path symmetry. The request or interest hops along the same path, well, in reverse, that the content takes. Today's internet does not guarantee that. Right? You can send a packet from A to B, and it will take one path, and the reply from B to A can take a completely different path. In fact, two successive packets can take two different paths. Right? The internet today is very libertarian. It doesn't guarantee anything. Whereas here, there is a built-in symmetry. Is it always a benefit in terms of performance? Certainly, if packets follow, requests and responses follow the same path, there is some predictability. So there is potentially some benefit, but it's not clear. The other question is about flow and congestion control. Where and how should it take place? Today, flow and congestion control is done very much ad hoc. At the end, right? TCP, most of complexity of today's TCP is due to flow and congestion control. And finally, well, almost finally, security. Now, what attacks are obviated or prevented by this architecture, and what new attacks are prompted? And this refers to the question that the gentleman in the back asked. And he already made sort of a hint towards one possible attack. And then this interesting feature of interest collapsing. It's very appealing. When I first heard of it, I thought, that's a great idea. Because if you really have massive number of simultaneous requests for the same content, this interest collapsing must be super useful. Must be a great way of reducing congestion. But like any tenet, it should be questioned. Does it actually happen? Would it actually happen? How much of a benefit is there? So let's look at the reverse path forwarding or the symmetric forwarding. Some internet applications are by their nature distributive, unidirectional. Meaning that like the web today. You typically go to the web server. Let's say you go to Gazzetta dello Sport or whatever, whatever you read, Veneto Oggi, right? And you go to your favorite website. You typically don't upload much information, right? Unless you're filling out some forms, which is rare, right? Most of us tend to pull information so that there's an asymmetry, right? There's a very little information going up from our client browser and lots of information coming to us. So it's a distributor, right? And most of the time with notwithstanding some ads or personalized stuff, most of the time the information is generic, right? It's the same news story that I will read that you will read. Okay, so these kind of applications, and it's not the only one, right? You go to Facebook, you go to Twitter, YouTube, you're pulling down the same content other people are pulling down. So these applications are distributive, and they're unidirectional, meaning that content typically flows one way. Requests go up, content comes down. And then other applications are bidirectional, like teleconferencing, video conferencing, remote login like SSH type communications, P2P communication, they're bidirectional. So for such communications, you need routing to both ends, right? So what I'm saying, if you have unidirectional communication, you only need routing towards the producer of content. But if you have communication flowing in both directions, like let's say Skype type communication, right? Then, or any kind of voice over something, then you need routing to both ends. Okay, so there's less of an incentive to use reverse path forwarding. Furthermore, if you already have forwarding to both ends of the connection, the state or the information in the routing tables, what's called fibs, already subsumes information in pits, right? Because in some ways it can be redundant, in particular for bidirectional communication. The other thing is that path symmetry is not universal. This has been studied, in fact, among other things, in this interesting little paper. It's more common at the edges of the internet than it is at the core, in the middle of the internet. And the other thing we should notice is when we introduce this new state, this new data structures into routers. Now, remember routers, and I'm sure some Cisco people here will agree with me, I hope. Routers are busy bees. They are busy bees. They're supposed to, they have one job, one main job, forward packets. Anything else, like, I don't know, watching a movie, picking fingernails, verifying signatures, I don't know, fetching public keys, that's not their job. That's overhead. That's pure overhead. The really useful part of a router is forwarding packets really, really fast. Everything else is boring and it's overhead. So let's look at what happens when the overhead that is introduced by these kind of data structures, by the pits and the caches. The total transaction cost for a given router, for one router, to process an interest packet and a corresponding content packet. Well, let's see. It takes 2 pit lookups, 1 fib lookup, and 1 cache lookup. That's the overhead for a router. There's computational overhead. So why 2 pit lookups? The first one happens for an interest packet when it comes in. The second happens for the content packet when it comes back. because you need to associate the content with the PIT entry. The fib lookup happens for an interest packet when the interest packet needs to be forwarded. And a cache lookup happens also for the interest packet at first to see that whether it's in a local cache. These are not negligible operations. Of course, with some very expensive and customized design, you can make these things very, very fast. And maybe here routing manufacturers are not so upset because actually it allows them to build new sexy little features into their routers and sell routers for a bit more than they do today. So there's a trade-off here. But it is overhead. And in particular, these PIT lookups, they're not free. I mean, they can be made cheap with expensive memory, associative memory, but they're not free. And so this table, I'm not going to bore you too much with this table. This is the results of a simulation that shows that actually, you know, despite kind of the size of the PIT, the lookup is always going to cost you something. In particular, in our simulation, it costs you like roughly 4.5 microseconds. Now, microseconds, right? Not hours, not minutes, microseconds. You might think this is not a lot. But I'm sure there are people smarter than me who are actually closer to building actual routers in this room, maybe, that would probably say that this is not negligible, that this is quite a substantial overhead, if it is indeed, if you believe simulations, right? This is another issue. If you believe simulations, 4.5 microseconds is definitely not negligible. Now, as far as flow and congestion control, today, it's moving more towards the receiver, right? So, and if we follow the same kind of a paradigm, then we will need to store per link congestion control in the PIT. And this is a problem, especially, or particular, because if you notice, the interests and the content, they follow the same path, well, in reverse, but there is a big size difference. So if you, let's compare it, for example, to something like remote login or voice conferencing, where packets go back and forth and they're roughly of the same size, voice packets. Or remote login is like one character at a time is a packet. But with this kind of architecture, where you have small interests flowing one way and potentially unlimited or very large content flowing the other way, there is a size disparity. And so it's not clear how to do congestion control effectively. And this has been explored among in this literature. And then security, right? So every interest leaves some state in a router. Yes, even the ones that get collapsed leave some state because the router has to add their incoming interface to an existing PIT entry. What's nice about this architecture, and there are some very nice features, one of them is the fact that a consumer, that is, like, say, somebody like you or me, sitting at home, consuming content, like browsing the web, today we can be attacked, right? Because somebody can see the exit address, let's say our home cable router or home ADSL modem. The IP address of our home essentially gets reflected in the source address of all IP packets, right, coming out. But in this architecture, if you're a consumer sitting at home issuing interest for content, let's say reading articles on the web or browsing Twitter or whatever, you cannot be attacked. That's a very nice feature. And see, the reason you cannot be attacked is because you don't exist as an entity. You don't have an address. In order to be attacked, somebody has to be able to forward you traffic. But if you don't produce content, you don't exist as an entity. You only request content. And if you request content, of course somebody can send you bad content. But only when you request it. If you don't request it, nobody can send you anything. Because one thing I forgot to mention, and maybe it should be, it is already obvious, is when a router, anywhere on the internet, when a router receives content and it cannot find a PIT entry, it throws that content away. Does that make sense now, right? That it's impossible to send unsolicited content to a consumer in this architecture. And that's probably the best feature, right? It really is a benefit over today's internet. Okay, now the bad news is that because of this new state, because of the PIT and the cache, these new resources that are introduced into the routers, we know for a fact that anything new or any resource will be abused. And so, thinking about security, we have to anticipate attacks, right? Rather than work like in today's internet, which was designed for a friendly, chummy world of thousands of academics. Nobody expected it to grow into this worldwide phenomena used by billions of people. But remember, it was designed for a friendly, small world. We know the world is not small and not friendly. So we have to think paranoid. Right? And so if you are thinking getting into security, think about being paranoid, at least putting a hat on that makes you paranoid. If you can't do that, don't go into security. Yes? No, it's what happens here is that the context-centric networking architecture will use some contortion, will contort itself to accommodate that kind of traffic. Like if you are the pusher of information, you would have to tell me to issue an interest for your information. So I request a request. That's right. Right. And this is how email works today, right? If you know how SMTP works, it pushes information. So it would have to be like, you would have to ask me, can I send you email? Or could you please fetch my email that is for you? It's a bit strange, but it would work. It would involve some overhead, right? So naturally, the only strong point here is massive scale content distribution. Everything else has to be somewhat, perturbed. Okay, so as I said, any state will be abused, can be abused, and will be abused. That's not a question. It's not an if and when. It for sure will be abused. But how? So one type of an attack, I'm not going to talk about it. It's not as interesting, but I should mention it, is content poisoning. This is when a consumer requests some content and some bad actor, some malicious router, or some interloper in the middle of the network injects poisoned content, that is fake or incorrect content, in response to a legitimate interest. Okay? This is a problem. It's not a huge problem because, of course, the consumer, when it will receive that content, will verify signatures, detect, and throw it away. It can be a bigger problem if a consumer consistently receives bad content, because also remember, routers are supposed to cache things, right? Routers cache content. And caching is a way of amplification of poisoned content. Right? If a router caches content that is bad, that is incorrect, now all the subsequent requests for that content will result in incorrect copies of the content propagated. So it's kind of a nice way of amplifying bad content. Now, routers are supposed to verify signatures as well, but this is a problem because it's not their main job. Because verifying signatures is, well, much more expensive than doing a PIT lookup. It's not, probably a few microseconds, okay? So there is a problem. This is content poisoning, but it does have a solution. If routers verify signatures, there is a solution, and if you're interested, I can point you to a solution. What does not have a solution is this first attack, interest flooding attack. And what it targets are routers and producers. It doesn't target consumers. It targets producers and routers, more specifically routers. Right? So let's take a look. What is interest? Ooh, that does not look good. Hold on. Let's do some real-time repair. This will help. Okay. So what happens here is the adversary generates numerous, when I say numerous, massive amount of nonsensical interests. But they're not completely nonsensical. They are composed of two parts, the sensible part and a nonsensical part. The sensible part corresponds to a legitimate producer prefix. This is the blue. Okay? And the nonsensical part is the suffix, which is just any kind of random string. This is trivial to generate. It costs nothing to generate these kinds of strings, right? And if you stick this into an interest, what is guaranteed to happen? It's guaranteed that the network, according to the rules, will propagate this all the way to the producer. In this case, me. Right? And in the process, it will consume resources. And it's a very beautiful attack because it's asymmetric. Right? This is the best type of attack. We don't care about attacks that require huge investment from the adversary and the payoff is small. The best attack are asymmetric, kind of like terrorist attack, asymmetric warfare. Invest very little, get a lot in return. Here, the damage that the attack causes is much greater than the investment the adversary puts in. So, it is trivial to mount. Consider something like a Mirai botnet, right? Remember a year and a half ago, Mirai botnet, a bunch of consumer smart home cameras have been infected and then used as zombies to mount massive distributed denial of service attacks. The same scenario would work beautifully for interest flooding. Okay, imagine millions of little amoebas generating nonsensical interest against, I don't know, Sony, Google, Padova University, whatever, you know. This would cause tremendous damage, right? And as I said, it affects routers and producers. Of course, routers are more important than producers. So potential countermeasures include limiting, throttling, all kinds of things. And I see that I don't have a lot of time, so I better speed up. They have very partial effect. So there's no actual wholesome, deterministic countermeasure against these attacks. Best you can do is monitor some failure rates or satisfaction rates for interest, try to push back and throttle traffic. In the process, you wind up punishing good traffic as well as bad traffic, because fundamentally there's no way to distinguish nonsensical interests from sensible interests. Simply that, because a router cannot tell the difference. All right, let's zoom in. What is the anatomy of an interest flooding attack? Right? Anatomy of damage. There's three types of damage that it causes. One is processing in routers, the second is state in routers, and the third, well, bad numbering here, and the producer processing. So the most important is router processing. This is every interest coming in has a PIT lookup, cache lookup, fib lookup, and new entry insertion. Now notice these are nonsensical interests, so they will never succeed in lookups. Right? There's a random string appended at the end. You will never find it in the cache. You will never find it in the PIT. It's guaranteed to have a miss in both cases. So you always have a lookup of a PIT, lookup of a cache, lookup of the fib, which will succeed, and an insertion of new PIT entry. Those are four tasks that are not negligible. That's quite a bit of work for a router. The second problem is router state. Right? It has to insert a PIT entry and it has to maintain it, because it will never be satisfied, right? This is a nonsensical interest, which means it will expire. So it needs to be flushed at some point. And last but not least, there's producer processing. When an interest comes into the producer still has to do a cache lookup, because at the network layer, that's what you're supposed to do. And if it fails, if it doesn't find anything in a cache, it is supposed to invoke the application that sits on top, right? Like web, voice over something, okay? And so, but it means the application will receive the nonsensical interest and will say, ugh, I don't know what this is, and throw it away. But that's work. So it goes through the network layer to the application. That is overhead. So that's bad. Now, let's look back at interest collapsing. Does it actually help? We did some simulations. actually my students did some simulations, and if you believe simulations, and I don't know, this is a big if, right? I personally always take simulations somewhat skeptically. Interest collapsing isn't a very common thing. Now, we cannot say that with absolute certainty because we do not have an internet operating using context-centric networking. Right? We can only suppose that it will not be very helpful. So what we do is suggest an alternative. Okay? The alternative is strange and a bit anathemous to the sort of more orthodox context-centric networking design. Instead of having a pit, which is the main problem with the main issue with overhead introduced by this interest flooding, this nonsensical interest, we suggest that there will be no pit, or at least for certain types of traffic, no pit. And instead, every interest should carry something called RBN, or routable backward name. Now, there's a bit of a departure from what I described earlier. The idea is that as the interest propagates through the routers still look up caches and are still capable of replying if they find the desired content in the cache. But if they don't find it in the cache, they don't store any state. They forward it on, and when the content is found, either in a cache or at the producer, it is routed back with a particular address. That is the address of the consumer. This is why it's called routable backwards name. So essentially, what we do is we say content becomes a kind of an interest. Right? We attach an address to the content and say, send it there. The implications are kind of grave. It also it means now that every consumer who wants to receive content needs to have a name. Doesn't need to have a public key, right? Doesn't have to generate content, but it needs to have a routable name, which is a change, right? So now, an interest packet would carry a content name that it desires and a routable backward name where to send the content. And then the content packet coming back would be addressed to this RBN and will also carry the content name. There's no need to sign anything from scratch because the content can be already pre-signed, right? In particular, this field here doesn't need to be secured. The main effect of this design is the fact that there's no pit. Because there's no, if you don't have something, it cannot be abused. That's kind of an axiom. So this does mitigate some of the effects, in fact, the most grave effects of interest flooding attacks. Why? Because there's no pit lookup, there's no state, there's no insertion of new entries. Interest flooding can still occur, but it doesn't cause as much damage. So now what happens is that when a pseudo-interest is a junk interest arrives into a router says, let me do a cache lookup, doesn't find it, it then forwards according to a fib lookup. So there's still overhead, but it's much less than before. An unfortunate side effect is now the consumer becomes addressable. If somebody sees a routable backward name and wants to abuse it, they now can. It's a trade-off. So the interest format then becomes like this, right? We just add a new field. Content format becomes like that. Again, add a new field. The stateless data plane still works the same way as before, except there's no state anymore. Okay, now the path taken by a content and path taken by an interest can still be the same, but they are no longer obligated to be the same. There is no mandated path symmetry. One of the areas where this might be useful is in mobile networking, where you have a mobile consumer, right? What happens with mobility or endpoint mobility is if you request content, by the time it comes back, you may be in a different place. So if you know where you're moving, you can always give a routable backward name in a way that still allows the content to find you as a consumer. Now, we are not suggesting this actually as a complete replacement for the stateful data plane. One observation we make, and it's an obvious observation, is that this approach is not mutually exclusive with respect to stateful forwarding that I described and criticized before. Those two can very well coexist in the same router at the cost of some more complex implementation. In fact, an application, a given consumer application, can choose to use either stateful or stateless forwarding. For example, what is the point? Let's say if me and this gentleman here are engaged in a voice conversation over the internet, there's generally no point to do pit collapsing because it will never occur. It's a private conversation between us. Nobody else will be requesting our packets. Okay? So using a pit for that kind of communication is useless. In fact, using a cache is almost useless as well. So if we allow applications to choose either stateful or stateless forwarding model, that's like freedom and democracy for all. Yeah? Lots of choice at the price of slightly more complex router implementation. So one can imagine sort of this fairly obvious hybrid. Or you can imagine statefulness at the edges of the network and then stateless design in the middle. One of the reasons for believing in this model is that there's some credibility to the idea that even if content-centric networking takes off and takes over the internet, it will never be caches and pits in the middle. That the routers in the core of the internet will always want to be as high speed as possible, and all this nonsense about new data structures will be kind of deprecated. So, but it is possible to imagine the design where the core of the internet is stateless and the edges of the internet, that is ISPs, etc., are stateful. This needs to be explored further. All right, I'll just try to speed up here. I have only a few minutes. Let's see. Yeah, so this is what we call application apartheid. Right? Separate but equal. That is, every application chooses its own, or even consumer. Right? We can even make it really, really granular and say the consumer can choose for a given content. Even within the same application, the consumer can choose whether a given request, an interest, is a stateful interest or a stateless interest. We did some experimental assessment, which I will not bore you with, but I mean, only to point out that, again, simulations, right? But with reasonably credible simulators and well-accepted traffic models, that actually stateless processing, which you see here in green, is a lot faster, right? Clearly because we avoid pit lookups and insertion of pit entries. So I'm going to skip that. Wrapping up. Well, statelessness is good. Statelessness makes it harder to mount asymmetric attacks like the interest flooding. It triggers some new issues. Any new feature can and will be abused. And of course, if we introduce the stateless design that is advocated in this presentation, we will pay a price. In particular, consumers will become addressable. We believe that there is some bright future for maybe hybrid deployment. Now, I know that some players, maybe Cisco, is working on hybrid CCN, which is a little bit different. The word hybrid for them means something a bit different, but hybrid of CCN/IP. But maybe hybridization within CCN itself is a possibility for the future. It's also possible to imagine completely cashless operations, right? CCN does not imply caches, so you can imagine completely stateless routers with this approach. We provide fairly low overhead with respect to stateful variant. And we also note that there are some other approaches that have been suggested by other groups, other researchers. In particular, there's a very interesting approach that, I think I have it in the next slide, that is in the third item from the top. There's a paper by Alston et al., and it is poorly written from a security perspective. So if you're a security person, don't take this paper seriously, but it does suggest a very interesting networking approach, sort of a mitigation to interest flooding attacks. And what it suggests, instead of using routable backward names that we explore in this presentation, this paper, what they suggest is putting state on the wire. So this is a well-known concept in networking, but here's how roughly how it works in their approach. They say, instead of having a pit, let's take the information that would be in the pit, attach it to the interest packet, and send it on. I hope you're following me. So remember how the pit works, right? They do everything that you would do with a pit, except that they create a new pit entry, but they don't store it. They say, let's attach it to the interest packet, or prepend it, and send it on. And so if you follow this chain of reasoning, what happens is an interest packet still hops around through the routers, but it doesn't leave behind any state. Instead, that state is accumulated in the interest packet itself. Eventually, when that interest packet arrives finds the desired content or arrives at the producer, it is then reversed, and the state accumulated in it is copied onto the content. Okay? So now content hops back along the same path in reverse. And every router remembers, oh, this is the pit state I appended to the interest. So it's a very cute approach. It's probably unrealistic, but it's very, very nice, and it's worth exploring. And let's see what else I was going to say here. There's still lots of uncharted territory. So if you are a networking person and you're looking for new things to do, CCN is a treasure trove of issues, problems, interesting things to do. Thank you. Stateless forwarding approach similar to IP forwarding? Yeah, I mean, it is trying to essentially keep content centricity of this architecture, but kind of married to IP stateless approach. Yes, that's exactly right. No. No. Nobody has ever done. You can't, right, unplug the internet and reboot it and expect that everybody will live happily thereafter with CCN. Look at IPv6. IPv6 is a simple extension of today of IPv4. It's been over 20 years since it's been proposed. How many people use IPv6? I mean, most people don't even know what IPv6 is. Now, the truth is, you're at the university, you probably, like me, you are using IPv6 sometimes, because most of the equipment we have, whether smartphones or laptops, they support IPv6, but it's used for a small fraction of communication. So if you look, okay, realistically or pessimistically, if IPv6 fares so poorly as far as adoption, what hope can we have for CCN? Okay, so I don't want to be a pessimist, so I'll tell you this. I think that the hope for CCN is it could see some deployment at the edges. Like you could create a private network, what we call a stub autonomous system that is entirely CCN. And then put a gateway at the border that translates CCN traffic to IP traffic. I could see that happening. I could also see the core of the internet, this is less likely, but I could imagine the core of the internet changing to CCN, okay, and the edges remaining IP. That could also happen, okay, with some gatewaying, of course, which would not be trivial. But I don't see it taking over the world like some new religion. No. You remember my comment about the dirt and the rug. Okay. Well, I don't think this is a new problem. It's not like CCN is the first one to have this problem. We have this problem today with the web. you see? I mean, how, you know, we think the web is moderately secure, right? But I'm sorry. Right. So let me describe in a few words one way to kind of address this problem. So I don't know how to address the PKI, which is public key infrastructure problem. That is a problem that exists today in email, in the web, in SSH, and a few other things. It's not a new problem. If we solve it in one instance, we'll solve it for all. So I don't know how to solve that problem, but I know how to solve the problem I think that you are referring to. And that is if we say, look, every router must, when it receives an interest, right, when it's an interest for content, it must know what the consumer wants, meaning which public key the consumer expects to sign the content coming back. Okay? It's not unreasonable, because the consumer should know who is the producer and must know the producer's public key. Kind of like in SSL, TLS SSL today on the web, we know the public key of the web server. Okay? So if the consumer can tell the routers as part of the interest that, by the way, I'm fetching a content from CNN, and I expect the content coming back to be signed by CNN's public key, and this is the digest or reference to the key, then the router on the way back can make sure, right, by verifying one signature, at most one signature, that the content coming back is signed by the right party. It already makes sure, without security, it already has to make sure that it has the same name. But in addition, now it will verify that it's actually signed by the right party. That mitigates content poisoning attacks. Okay? So it would work. But I understand and I acknowledge that we still have the PKI problem. That is, how does the application allow the consumer to learn the correct public key for the correct producer? That remains to be a problem.
Okay, so now we have a short 15 minutes break with a coffee break actually outside. So.